Cool. B6. B6, which of the following buffer systems would be the best choice to create a buffer with pH of 7.20? Explain. So, one thing about buffers, right, is that you want to have the pKa of the conjugate acid base pair to be, within 1 of the pH that you're aiming for, right? The closer it is, the better, because it'll be a lot easier to really form that buffer and have that buffer stay close to that pH, because in that case, right, the closer it is, the less difference you have to have in terms of the number of moles of each one of the different reagents. So all we really have to do in this case is figure out what the pKa's are of each one of these pairs. So if we're looking at this right here, right, what we have is this Ka value for this set, which is, what is that? Formic acid and sodium formate, right? So we're given the Ka value of 1.8. So if we figure out what the pKa is, right, and the pKa calculation, right, is just simply negative log of the Ka. So if we do that calculation, what we get is negative log of 1.8 times 10 to the negative fifth. So this has a pKa of 4.74, right? The next set that we have is the ammonia ammonium chloride set, right? And so this gives us a Kb. It doesn't give us a Ka value. And so what we have to do in this case is make sure that we convert that into Ka in this case. But one thing we can do too, right? I didn't have it this week. I had it last week, right? But I think one of the things that I asked all of you to do was kind of like make a lot of different relationships between different values. And so what we can easily do, right, is that we know that the pKa of something and then the pKb of, right, the conjugate base, right, those are going to be equal to 14. And that has to do with the fact, right, that the negative log of Kw is going to be, the negative log of 1 times 10 to the negative 14 is going to be equal to 14. And, we can then easily set up that relationship there. And so if we know that the pKa plus the pKb is going to be equal to 14, we don't have to do any kind of conversion really of the Kb into Ka first, right? We can just simply plug that directly in. And so what we can do here, right, to figure out the pKa is we can just simply derive this and have this just simply be 14 minus the pKb, right? And so what that would then be is then 14 minus the negative log of the Kb, right? And so then those negatives cancel. So it becomes 14 plus the log of Kb. And so if we do that, uh, 14 plus the log of, right, and the Kb in this case is 1.76 times 10 to the negative 5, right? So that comes out to being 9.25, right? So that's what the pKa is for the ammonium chloride in that case, right? So that would give us an idea for that buffer. And then for the hypochlorous, the potassium chlorite, one, right here, the pKa now is going to be equal to the negative log of 1.1 times 10 to the negative 2. So that is 1.96 in this case. And then the Ka for the HClO and potassium ClO is going to be negative log of 2.9 times 10 to the negative 8. So that comes out to being 7.54. Right. And so if we're looking for something that has a pH of 7.2, right, that's the buffer that we want to make. The pKa that's closest, right, is the one that's 7.54, which is the number 4 right here, right? And so that's going to be the best one to use to make a buffer with that pH, right? So you have to take into account what the pKa's are, because you don't want to have the ratios be extreme between the different values, right? You want them to be as close as possible. And the best ones you're going to do is always going to be the ones that are, within 1, unit of the pH. So that's B6.